Hello, everyone. Today it's not our closing day, so thank you all of you uh, for watching our talks. So we are very happy to organizing this event. And before starting our talk, we have some videos from our sponsors. Okay.
Good morning, my name is Paolo Gamba and I am the president for the year 2020 of the Geoscience Remote Sensing Society. Okay, so first of all, what is a scientific society? What is GRSS? So a scientific society is a group of scientists, researchers and practitioners with common interest and common framework for building a community. In our specific case, we are people who are dealing with theory, concept and techniques of science and engineering as they apply to remote sensing of the Earth, ocean, atmosphere and space, as well as the processing, interpretation and dissemination of this information. So what are the activities of the IEEE Geoscience Remote Sensing Society? Well, we have a number of applications. We support conferences. We have professional activities. We have a number of information service and technical activities and education activities as well. We are a global community, which means that we are arranged around a large number of groups of people that we call chapters all around the world. We have currently more than 90 chapters all around the world. As a result, GRSS disseminates premium science by means of its three main journals, which are the Transactional Geoscience Remote Sensing, the Geoscience Remote Sensing Letters, the IEEE Journal of Selected Topics in Applied Earth Observation and Remote Sensing, but we have also a magazine, which, by the way, has a very, very important role. We also provide opportunities for the different communities, like, for instance, the community working on image analysis and data fusion. We also sponsor community-driven events, like the very successful Earth Vision workshop, but also the SpaceNet Challenge Data challenges here, which is organized by SpaceNet. We support also community-developed tools like the DESE website, which is Data and Algorithm Standard Evaluation website, and also activities related to RFI observations. So we also facilitate and connect. We have a number of activities at in our main conference. We have the so-called TIE events, but we also organize different events related to connection with companies, industries. We have a number of activities like for young professionals, for women in engineering and in geoscience and remote sensing. And we share our knowledge on hot topics by means of distinguished lecturers and industry speakers. We have also a number of educational activities. This is one of them. This is basically, let's say, one of the many different small educational videos for kids that we have in different languages, but we have also, in addition to that, a number of webinars, which are also for people who are not kids, about remote sensing in different languages as well. We offer continuing education by means of webinars, which is especially important and useful in this situation where we are not able anymore to move around the world as we were in the past. So we can support continuing education of students and young professionals through conferences, journals, our magazine, webinars, and so on. We can promote capabilities of the different communities, algorithms, data set by means of the data fusion context, by means of dedicated events at our conferences, by means of the industrial distinguished lecture or industrial speakers. We help connect companies and young motivated people by means of the young professional event, by means of student grants, by means of the TIE forum. And we make the different community of Earth observation practitioner and researcher be aware of their and your topics of interest. So GRSS is actually a community of communities where we could together share and promote ideas, systems, and data set. We can meet with other communities and gain from their perspective, and we can build different collaboration to learn more from each others and to come together in conferences. Thank you very much, and I hope you will enjoy this summer school and all the interesting topic and talks that you are going to listen during these days.
Thank you, Paolo. And now we will have a video from our other sponsor, ISPRS.
Hi everyone, my name is Cheryl Rose Reyes, and I currently serve as the president of the International Society for Photogrammetry and Remote Sensing Student Consortium. I am very happy to welcome you all to the 6th edition of the IEEE GRSS Young Professionals and ISPRS Student Consortium Summer School this year. To start this event, I would like to present a bit about the ISPRS Student Consortium. We are the official representation of the youth to ISPRS. We link students, young researchers, and professionals worldwide interested in photogrammetry, remote sensing, and spatial information science to promote their scientific and professional developments. We advocate imaging and geospatial science for informed, scientifically valid, and technologically sound observations of Earth conditions and trends that lead to improved and effective decision-making. The consortium is also accepting registrations for individual membership. Please scan the QR code in this slide if you are interested to join us. I work together with members of the board of directors from all across the globe. Charles from Uganda is our vice president. Charmaine, who is currently in Ireland, is in charge of our newsletter. Mustafa, our social media administrator, is from Turkey. And finally, Sona from Azerbaijan is our web administrator. One of the major events that we host and coordinate every year are the summer schools. In 2019, the summer schools were in Uganda, Poland, South Korea, and Brazil. These summer schools provide international learning opportunities for students and young professionals at a minimum cost. This year, we scheduled 3 summer schools, but due to the COVID-19 situation, 2 of them were postponed, and we are sincerely thankful to the organizers of this summer school for making this an incredible virtual event. This is the first ISPRS Student Consortium Summer School that will be hosted online, and as you can see, we have an amazing lineup of speakers who will deliver lectures on remote sensing and machine learning. The consortium currently hosts the virtual rooms and the webinar series to provide our community with more opportunities to learn and interact with experts in our scientific community. The webinar series was conceptualized in 2018, and we have organized webinars on Google Earth Engine, computer vision, and machine learning. The virtual rooms is an initiative to keep the members of the consortium connected during this challenging time and to help them navigate our changing lifestyles. All the resources for the webinar series and the virtual rooms are available on our website and our YouTube channel. We also publish an official newsletter called Spectrum, which covers the broad applications of remote sensing, photogrammetry, and spatial information science, and welcomes contributors from diverse backgrounds and disciplines. We publish 4 issues a year, and our most recent issue is related to the current pandemic and the significance of geospatial information in tackling the impacts of this global health crisis to our society. The ISPRS Congress is one of the biggest gatherings in our scientific community, which is held every 4 years. The Congress hosted a virtual event for all papers submitted this year and postponed the in-person meeting for 2021. During the Congress, the consortium will be hosting a 3-day youth forum, which will feature the following activities: speed dating, technical sessions, a special session on women in remote sensing, photogrammetry, and spatial information science, a panel discussion, the General Assembly for our members, a student night, another summer school and will co-organize a mapping party. The consortium would also like to invite you to nominate papers for the Excellence Award to be given during this event. Please scan the QR code for eligibility and nominations. Also, please visit the ISPRS Congress official website for updates. Finally, I would like to invite you all to join our communities on Facebook, Twitter, and to visit our website for all the information shared in this presentation. And again, I would like to invite you all to register as an individual member by scanning the QR code on the right. This is the end of my presentation, and I wish you all a meaningful summer school. Thank you very much.
Thank you, Cheryl. So at this moment, I would like to invite our chair, Rosa Pabon. Hello,
Hi.
Rosa. Thank you very much for accepting to coordinate in this session.
Thank you for the invitation.
So the room is yours.
Okay, thank you. So I'm going to start. Hi, everybody. Good morning, good afternoon, good evening. It is a pleasure to have you with us on this last day of the 2020 Brazilian edition of the IEEE GRSS ISPRS Young Professional and Student Consortium Summer School. Today we are going to have 3 lectures, and this is the first one. With me there is Dr. Lenio and Jessica, who will help me with the sharing this section, and also Dr. Chabrillat, our honorary speaker. Before I start, I would like to introduce my co-chairs and also the speakers. Dr. Lenio Soares Galvão is a senior scientist at the Brazilian National Institute for Space Research, INPE, since 1925, with expertise in reflectance spectroscopy, hyperspectral remote sensing, multi-angle and multispectral observations. He has participated in several projects and campaigns using a great number of airborne, orbital, and tower-based hyperspectral instruments such as Aggeneys, HIMAP, AAS, ISAFENIS, CRIS Prova, and Hyperion EO1. Using these instruments, he has tested the hyperspectral technology for different applications in Brazil, over soils, crops, tropical forests, savannas, wetlands, and urban areas. And also Jessica Costa, this is our young professional today. She is graduate in environmental engineering from Santa Catarina State University, UDESC, Brazil. And also she has a master's degree in forestry engineering for the same university. And Dr. Sabine Chabrillat is senior research scientist at the GFZ German Research Center for Geoscience in Potsdam, Germany, head of the research group on hyperspectral remote sensing applications, and head of the GFZ Spectroscopy Laboratory. She leads a number of projects of retrieval of Earth surface composition from hyperspectral imagery based on laboratory, field, air, and spaceborne platforms. Besides, Dr. Sabine did her postdoctorate at the Center for the Study of Earth from Space, CIRES, at the University of Colorado, both the United States, and holds a PhD from University of Toulouse, France, on hyperspectral imagery analysis. So I will now to hand over to Dr. Sabine, who will deliver the lecture entitled Hyperspectral Remote Sensing Applications in Earth Observations. Dr. Sabine.
Thank you, Rosa, for the introduction. Can you hear me?
Yes.
It's correct?
Yeah.
Okay. So first, thank you, Rosa, and thank you to the session chair, Lenio, and the young professional, Sabina. And first, I would like to thank Veraldo and Jefferson for inviting me for this event. I was pretty excited that I can present this lecture on hyperspectral remote sensing. And since it's the first lecture on this remote sensing technique, I introduced some basics. First, and I have a focus on bare land applications. So, okay. So first, I will introduce a couple of definitions and also the physical background, like what makes that we can identify surface constituents from imaging spectroscopy. And then I will speak a bit about sensors, and in particular, I was asked to make a review of current missions, and especially forthcoming missions, because right now it's a big momentum for imaging spaceborne missions. And then I will present a few results of applications, and especially with highlights from the EnMAP program, and some perspectives and conclusions for the future. So first, what is reflectance spectroscopy? So reflectance spectroscopy, from definition, is the study of the interaction of light with matter. And here, this is Earth observation. So this is the analysis of solar electromagnetic radiation that is reflected by the surface. So you see the photons, they hit the surface. Some of them are absorbed and do not come out, but some of them come out, and those ones carry information on the material that they have been seeing through. And here on this signal, due to this interaction with the material, then the solar radiation signal is affected by some different shape, absorptions in the reflectance spectrum. And those shapes are actually characteristics of the material that is transported, in particular in terms of the nature of the element, in terms of chemical nature, like which atoms are in there, which cations, and the locations of those atoms in the atomic structure. And based on this property of reflectance spectroscopy, this technique is, at the definition level, is not a new technique. It's something that has been used since many years and widely used by inorganic chemistry for characterization of samples, by mineralogists, for planetary observations too, because it provides a unique information on the composition of the surface materials. So the historical development of techniques to put this type of data at the remote sensing level was the interest for reflectance spectroscopy for the study of planetary observations, which actually came before the Earth exploration. So in the 70s, there was constitution of databases in the laboratory of such data with a spectrometer. And this knowledge was the basis used to define the first spaceborne, the first remote sensing imaging spectrometers, like in '83. So you see this is now 40 years old, which was that the instrument must be able to resolve, if you see this kaolinite signature here. So this is kaolinite is a mineral that is pretty much white. And you see that at this precise wavelength, at 2.2 micron, so in a shortwave infrared, it has got an absorption band that is very characteristic with this double shape here. So the instruments must be able to resolve that doublet. So a bit of theory. So those spectral features in rocks and in minerals, in general, they originate from electronic and vibrational transitions. And those locations of these features at definite wavelengths, as I already mentioned, they derive from the characteristic of the crystal lattice. So like the coordination number, the nature of the ligands especially, and the nature of the central ion. So based on, thanks to this, mineral identification is feasible for, is well feasible for a couple of minerals, like the ones here containing molecules or anions like water, so liquid water, but also bound water. Some sulfates, carbonates are well identifiable from, and also some carbon hydroxene. And for example, say for lots of silicates like clays are very well identifiable from imaging spectroscopy. Hydroxides and wavering products, some sulfates, amphibols and carbonates. And for example, what you do not see on this list is silicates. Silicates are pretty transparent in the visible near infrared, and one has to look in the thermal infrared to be able to obtain those absorption bands from silicates. So a bit more in details. So in the visible near infrared spectral range, which is from 350 to 1000 nanometer, absorption features are due to electronic transitions, which means that the electromagnetic radiation excite some electrons that are in excitations level of energy, and they change transfer bands or through crystal field transitions. And those electrons are mainly related to iron in the B or trivalent state, so Fe2 plus or Fe3 plus. The absorption features that are in the shortwave infrared of the wavelength, so from 1 to 2.5 micron, are mainly due to vibrational effects. So now the electromagnetic radiations excite molecules, like 3 molecules with 1 central ion and 2 other molecules, and it vibrates. It's an auxiliary unit that is vibrating. Then there is emission of energy, and there is the appearance of absorption band. And in particular, we observe that phenomenon for all the molecules which are linked like a cation OH, like AlOH, so clay minerals, FaOH, and magnesium OH, and carbon O. So here an examples for iron-bearing minerals. So here we see, for example, goethite. This is the red one. Hematite, which are different products and different weathering levels of rocks, and ankerite and epidote that all have very different spectral absorptions. And you see that the center of the absorptions are different wavelengths, like here for goethite around 0.95, and another one around 0.7, let's say, and another one here around 0.5, which is not the case of the other two. So this is very characteristic. Here are a few examples with water molecules. So the water molecules, H2O, has got 3 fundamental modes of vibration, but in the thermal infrared range of the spectrum. And in the visible near infrared, we assist at the combination of fundamentals. And those combinations appear at several wavelengths, like here at 0.94, at 1.13, and 1.4, 1.9. And these differences allow also to identify the minerals. Like, for example, you see kaolinite here, which has no liquid water, but only bound water. So OH has only 1 absorption band at 1.4. And this is another reason, those water bands that allow to identify the water content into spectrum too. So now looking at clays, on the left here, you see the curves, all those different clays, kaolinite, pyrophilite, and muscovite, they all have absorption bands around 2.2 micrometer. So they have different bands at different wavelength in details and also different shape, but they all have an absorption bands at 2.2 micrometer. So this is really a characteristics of clay minerals, and this is something that with the hyperspectral technology works very well to identify clay content or the type of clay in a mineral or in a soil. And now the graphs on the right is MgOH bound minerals like saponite, talc, and serpentine. And you see that all of them have an absorption bands around 2.3 micrometer. So this is also very diagnostic of a mineral. Now, a last example for carbonates. Carbonates also have very characteristic signatures with an absorption band that is very wide, around 2.3 here. And you see, depending on which carbonate, there are actually small variations in the center wavelength, so that are in the laboratory would be diagnostic. And yeah. So now we move to soils. So soils are a bit more different. We can identify the same mineralogy from reflectance spectroscopy, but just the composition of the soils is a bit different. So here, all the soils have the same constituents. They have some iron, some clay, some organic matter, some water, some carbonates, maybe, but it's all mixed. So in soils, the problematic is a bit different. We have, you see, for example, so in the US, there was early works in the 80s from Stoner and Baumgartner that identified 5 spectral types in the US of soils. And below you see the figure for Benner and al. In 95 of a typical soil spectrum, where you see the different absorption bands. Like here, water at 1.4 and 1.9, some clay at 2.2, and the particle size influences the spectrum because it goes is more bright or more dark. The water content also makes the spectrum a bit darker, organic matter too. So in source, the effects are a bit one above the other. So in summary, for if we want to extract mineralogical composition, there are characteristic absorption bands that are well localized. And you see on the right some examples from the USGS spectral library with specific spectral signature. Now, if we want to identify moisture content or organic matter, there are also some specific absorptions, but there are also effects on the whole spectrum. Now, if we want to identify physical surface parameters like roughness or bone size, it's a bit, they affect the spectrum, but it's a more difficult the retrieval of this information. So if we want to identify minerals, we can do it directly from the location in wavelength for those absorption bands, the shape, and also the intensity. Is it very deep or is it just a bit deep? So for these softwares like analysis of the signal analysis works very well. Now, if we want to do surface physical properties like mapping organic matter, soil moisture content, it is also possible, but the access is a bit more difficult. It needs the whole spectrum and needs a different approach. Like, for example, for surface physical properties, some people do radiative transfer modeling, but mostly people do machine learning and this type of methodology. So as reference, we have several databases that are available from the web, but also every laboratory is actually developing his own references spectra. Also here, I named maybe the three most known. So the digital spectral library from the USGS, which covers from the visible to the thermal. They have thousands and thousands of spectra of minerals, organic and volatile compounds. They also have vegetation spectra and also man-made minerals. Then there is the ASTER spectral library that also covers until the thermal part of the spectrum. They have both natural and man-made materials. And then there is the LUCAS, the European LUCAS soil spectral library, which covers only the visible and the shortwave part of the wavelength range. And it's over the whole Europe, 22,000 points that were measured in the same laboratory. So one comment on those databases, they're all based on laboratory databases. That means that the samples are mostly powders. So it's not the natural state of samples in the field or what we see from remote sensing. So there are also more spectral libraries in developments from field signatures, for example. So here a few comments on that. So some challenges. Actually, for many minerals, the signatures are very close. So, for example, between kaolinite here and halloysite, you see you need to have a very good sensor to be able to see the difference between these two minerals. On the right is the same. Between dolomite and calcite, you have to have a sensor that has a very fine spectral resolution to see this difference. Now, on the bottom graphic between ferrihydrite and orange precipitate, the wavelength, the center wavelength is slightly different, and also the albedo. So basically, if we want to be able to differentiate these minerals, for example, we need to have a continuous spectrum, we need a high spectral resolution, and also a high signal-to-noise ratio. So those are high requirements. The second challenge is in the nature, things are not powders, and they all have this biocrust or mineral crust. And you see, for example, on the left, this it's a kaolinite rock, and you see there is from weathering this iron crust at the surface. And you see the red spectrum on the left is the spectrum of iron crust at the surface. And you see that in the visible in general, between the iron crust, the red spectrum, the blue one, the cut surface, and the green one, which is the mineral in powder, you see that in the visible range, the spectra are very different. But actually, what is very nice is if you look at 2.2 micron here, you see that they all have this kaolinite diagnostic spectral feature. So actually, this diagnostic feature is still allows us to identify the mineral even through this biocrust. And on the right, it's a bit different examples, but the same philosophy. So you have the exposed surface in red, the cut surface in blue, and you see in the visible, the spectra are very different here. But if you look at 2.2 micron, then actually there is some gypsum in this rock, because you see those different absorptions here, and also at 1.4, which is characteristic of gypsum. So we are able to see the mineralogy, although the effect of the surface. At the remote sensing scale, there is an addition of more effects. There is a signal degradation from the sensor characteristics, less spectral bands, more signal-to-noise ratio, and then there is the atmospheric and illumination conditions. We have to model and to retrieve the atmosphere, retrieve the parameters, and the signal is even more degraded. And then we have all the effects of the surface properties. So, for example, this biocrust and mineralogical crust that I was mentioning, but also we have a mixtures with vegetation, and you see here there's some spectra of green vegetation. So this is the top spectrum here, and the dry vegetation, which is the spectrum here. And actually, especially an arid vegetation, an arid dry land vegetation has a very close signature to a soil. So this is an issue that only hyperspectral can solve. And on the right, you see the issue of soil moisture. For the same soil, it affects a lot the signature. So let's go to the sensors now. So reflectance spectroscopy at the scale of remote sensing is called imaging spectroscopy, which is this capability of recent sensors. It's linked to a development in the sensor technology, that those sensors are capable for each image pixel that is acquired, that actually this pixel is acquired in more than 100 narrow and continuous spectral bands. So as comparison, Sentinel or Landsat have less than 10 bands or something. So here we are speaking of sensors where for each image is imaged in 200 spectral bands. And you see also on the right, there's a development of the technology. So those sensors nowadays are also available from drones. Like here, for example, with the VNIR from this Norwegian firm in the SWIR and in the visium and infrared. Those sensors are available from Airborne platforms, and in the future, or in these examples, in an upcoming Spaceborne platform. And also, you can use those sensors in the field and in the laboratory too. And now when you work with these types of data, when you work on modeling and multi-scale approaches, and also you develop laboratory and field measurements databases for calibration and validation. So as I said, now the data that the remote sensing imagery, the hyperspectral imagery, is we call that a data cube because of these 3 dimensions that are essential to hyperspectral remote sensing. So you have latitude and longitude, but then you have the spectral wavelength space, as we call it. So that means also the allocation of data pace. Each image is a very big in terms of data volume. And here, this is an example from the Aggeneys, the American imaging spectrometer. So comparison, what is a big gain in hyperspectral imagery on the right is that you have access to this continuous spectrum. Although with multispectral imagery, you have only access to, let's say, 7 to 10 spectral bands. And through this access to this continuous spectrum, then you can determine the mineralogy or some specific absorptions that are linked to the chemical composition of the surface. So here, this is an example of a few reflectance spectrum from the surface. So you see the blue one here, it's a clay, LOH is a kaolinite. The green one is actually a green leaf. You see the orange one is a carbonate, and the red one is an iron oxide. And you see the convolution from the spectral bands from Landsat in the orange and Sentinel-2 in purple. So you see effectively that hyperspectral, for example, for the kaolinite doublet, only hyperspectral can resolve that. Sentinel-2 and Landsat-8 with only one wide band at this wavelength range cannot detect from the signal kaolinite. And yeah. And for example, this figure shows also very well the input of Sentinel-2 if you look at the wavelengths around the visible and near infrared, around 0.6 and 0.7, how there are several narrow spectral bands of the Sentinel-2 sensors that then for the study of vegetation is very useful. And hyperspectral, of course, can do it. Right. So development of hyperspectral technology, so it started maybe 40 years ago in the 80s with the very first instrument in the US, the IS, but then the Aggeneys in the end of the 80s, which is still flying nowadays, but the Aggeneys has been a sensor that was improving every year, year after year, and now it's Aggeneys next generation with even improved parameters, which is a very highest quality sensor, I believe, nowadays. So the first airborne, now commercial, high-quality imaging spectrometers were in the 95 close to 2000, with especially the HIMAP sensor since 98, that is also still flying nowadays. The history of spaceborne hyperspectral remote sensing is not especially, has been very slow, let's say. So in the 2000, two sensors started, which both have open data policy. So the Hyperion sensor from the NASA, which was decommissioned in 2017, and the CRISPROBA from the ESA that is actually still in space. But both were technology demonstrator, could acquire only a few limited imagery and some issue with signal to noise ratio. And since then, there was some issues with technological and to put in space some sensors. So most people in the past 20 years still relied on a hyperspectral airborne campaign. So for this, there is a wealth of sensors around the world. Actually, we not go through it really. I mean, interesting, I think, is to look at the future now. So since 1 or 2 years, there's actually a wealth of spaceborne missions that have been put into space. And here I mentioned maybe the foremost important for us. So the DESIS, which is actually an American mission from Teledyne and linked with the German Space Center. So DESIS covers only the visible near infrared, but has got a very high spectral resolution, actually 2.5. I don't know why I wrote 3.3. The pixel size is 30 meters with a 30 kilometer swath. It is on the International Space Station, so that means that it can acquire only until latitude of 60 degrees and with a particular orbit. What is interesting is that DESIS, since very recently, has got a new open data policy. Then the next one is Prisma. It's the Italian satellite from the Italian Space Agency that was launched in 2019. And since May this year, it is in operational phase and actually has been open since the beginning of the operational phase as an open data policy, which means that anybody around the world can register, sign up, and request data. So this is for, I think, a big evolution for us. So this is, Prisma has got 2 sensors, one in the visible, one in the shortwave infrared, approximately 10 nanometer spectral resolution. It has also a panchromatic channel, also 30 meter pixel size, 30 kilometer swath. Then there is the Chinese satellite, the advanced hyperspectral imager on Gaofen 5, that was started also last year and is now in operational phase. And I know from contacts, let's say if you have contacts in China, maybe you can get some sample imagery, but so they are in operational phase for national users. And the Japanese sensors now, the Hisui, was put very recently in 2020 on the International Space Station 2. So it's the same limitations on the orbit. It is now in operational phase for national users, but they have said that starting next year, they will open for international users. So it's also something to look for the future, the Japanese mission. Now looking at the near future, we are looking at missions that will be launched in the next, let's say, next 2 to 3 years. So the EMIT, the NASA missions for mineral dust source investigations. This one will be put on the International Space Stations too. And this one is a bit particular because they will look at only spatial coverage only Earth. So they don't look at the whole Earth. They have special focus study area. They focus on arid land regions. They are a typical imaging spectrometer from 400 to 2500, 10 nanometer spectral resolution, and 60 meter pixel size and 80 kilometer swath. Then the EnMAP mission, I will speak a bit more about it. That is actually a coincident launch with EMIT. So this is very interesting for both missions here. And then there is FLEX, the fluorescence explorer from the ESA. This one is launched, planned in 2024. And this one is looking at fluorescence signal for vegetation analysis. So with much higher spectral resolutions focused on those spectral regions for fluorescence. And also you see the resolutions is much bigger pixel size. So now we speak about the next generation Landsat and Sentinel hyperspectral missions in preparation. So this is now a bit a different game because all the missions that I have presented until now, they are what we call target missions. Target missions means those satellites will not acquire over the whole globe continuously. It's not possible, it's limited from the download link from the satellite because of image data size. So all those target missions per day can only acquire a certain number of imagery. Now, these next generation missions, which are actually planned for the end 2020s, they are looking at global mapping. They will acquire over the whole globe regularly. And they will, so it is another requirement in terms of sensoric and compromise for spaceborne instrumentations. So first the NASA mission, so it's SBG, Surface Biology and Geology. It's a former ISPRS. So now has got nominated as designated from the observable study plan. And I think they have a very important deadline in a few weeks to see for the final confirmation that it's funded. So it's a hyperspectral imager from the 400 to 2500, but with 8 thermal channels. And the spatial resolution is 30 to 45 meter, 60 to 100 in the thermal channels, and they're supposed to have a revisit rate of maybe 2 weeks. And this one is driven by science objectives like volcanoes, snow, hydrology, natural hazards applications. The second one on the slides is SHINE, so it's a Copernicus candidate hyperspectral missions. It's one of the 6 high-priority Copernicus missions. Until now, the phase B2 has been funded and just started, which means that the industrial consortium is already in place, and the requirements also, and they start construction. So this one also is a hyperspectral imager from 400 to 2500. Less than 10 nanometer in spectral resolutions. We are looking at a typical Landsat pixel size of 30 meter, and also here a revisit rate of maybe 2 weeks. And here it's an operational Copernicus mission. So if you see at the thematic area, they are looking at the production of automatic algorithms to develop products. And these missions are looking at delivering what they call level 3 products, so soil maps, geological maps to users a bit on an automatic way. And as I said, these missions are end 2020s. Okay, a few words about the EnMAP satellite program, because we are running it here at GFZ. So this is an environmental mapping and analysis mission to study environmental changes, ecosystem, and natural resources. Something important for us because the science PI is at GFZ. I am actually act as the science PI since 2 years now, which means that we are responsible to organize the scientific accompaniment of the satellite and supporting the ground segment and the space segment for the future definitions of the mission. So this, the instrument of EnMAP now is finished and is in the last calibration phase of characterization phase of instrumentation. And end of the year, it will begin to go for integration in the bus and pre-launch activities. So that now makes a schedule with a launch in January 2022, so in 1 year from now, and after with a 6 months commissioning phase, and after the operational phase, it's open data policy. And there will be a portal for data requests that will be open before launch. So you see the mission, so there will be a 6 nanometer interval in the visible near infrared, 10 nanometer interval in the shortwave infrared. Equatorial crossing time is 11 o'clock, and 30 meter typical pixel size. And you see the limitations of data download. So with Nmap is maximum 1,000 kilometer per orbit, and maximum 5,000 kilometer a day as data acquisition. So as preparatory activities, we are doing many things, but let's say one of them is for the future exploitations of Nmap data. And we focus on this Nmap box that I really enjoy everybody to download, because the Nmap box is a free and open source plugin for QGIS. So it's implemented in the new QGIS. Be careful that you have to download the new QGIS free 16 version to download the last version of Nmap box. And plenty of tools for image processing, state of the art. It bridges GIS with hyperspectral remote sensing, and the GFZ is responsible for geological and soil applications in that algorithms. So now a few applications. Sorry. My apologies. I wanted to present a few applications, and I'm here on mineral explorations and geological mapping. And here I find those applications the most impressive mineral maps, and that demonstrate also those large-scale mapping that we will be able to do in the future. And on the left is a mineral map of Australia based on the Aster imagery by Saro. And on the right is a mineral resource map of Afghanistan, which is based on airborne imagery, so from HiMap imagery, with 200 flight lengths, which is a very impressive work. And all these works led to some discovery of mineral exploration study area. And here an example of this mineral map that was made of a scale of country level, like Afghanistan, with carbonates, phyllosilicates, so clays, sulfates, and some hydrations. So it's a very interesting work. And I think it's a demonstration of what is possible from future satellites, or what is to be expected. I like also very much these examples of mineral exploration. So this is one of my colleagues at GFZ that is doing it thanks on reflectance spectroscopy. You see those minerals, jarosite, hematite, and goethite, which are iron oxides from low pH to neutral minerals. They are symbolic of a certain environment. And in particular, for people looking at oil explorations and looking at identifying of targets of exploration zones, those minerals are, especially if they are found in a certain order, then they are typical of these high exploration zones targets. And here this is a work that was made in the Aggeneys mine, so in South Africa. And it's interesting because on the left, it's looking at a new index with iron feature depth from Landsat 8 data, which in the first step for mineral exploration would allow to identify iron-rich areas. And then in the second step, so on the right, hyperspectral imagery. So here this is based on Hyperion data. So in the second step, Hyperion imagery is able to identify those different minerals, hematite, goethite, jarosite. And if these minerals are in a certain sequence, then it allows to identify that we are close to, let's say, potentially our exploitation zone. So those are hyperspectral has been very high on the agenda of mining exploration companies because of these capabilities. And the second high capabilities is the same idea, but is the monitoring of the mines at the end of the life or through the life of a mine. And examples, and especially here looking at contaminations, like after the extraction of a mining product. And here this is an example that was made in the Czech Republic from Veronika Kopakova. And we have long-term extensive lignite mining and with now some issues in terms of heavy metals contaminations. And here, based on those characteristic signals of those pH minerals, they're able to make a spectral modeling of pH estimation and to make a map of quantitative pH over the mines. So here another example. So this was made by me several years ago in Colorado in the US. We are looking at swelling soils. So swelling soils are soils that when they are wet, they swell the volume. And in terms of natural hazards, swelling soils is in the US a very high hazard in terms of damage to buildings and to infrastructure and to cost to the government and federal institutions. So it has been a big momentum to identify those areas of swelling hazards. And here, in terms of mineralogy, it looks like smectite mineral. So this is the spectrum now in red. Is a mineral that is responsible for most of the swelling soils hazards. And you see in the map on the right, we can very well identify those areas with the smectite rich. Those are the red areas in comparison to the yellow and green areas, which are less smectite rich, so then less swelling. So this has been a successful application of technology. The next successful applications of the technology is issues with food security and soil resources, and looking at soil health and soil quality and soil protection. And here this is an example with clay percent, so textural parameter of soils. But soil fertility is linked to this parameter. And here you see on the left an airborne of an examples of a mapping of clay content inside the pixels. And on the right, it's the simulations of an Nmap sensor. And we're validated with ground truth. And you see that we have some loss in the accuracy of the modeling from airborne to satellite because of a loss in the spatial accuracy mostly, not because of a spectral sampling. But it is still quite an accurate prediction. And maybe an announcement here, if some of you have airborne hyperspectral imagery and they would like to have a spaceborne simulation of Nmap, still in the waiting time that data is available, we can run it here for you. So just contact me and we can do an Nmap simulation for you. Here we were looking at soil organic carbon. So organic carbon is one of the essential climate variables in the list of essential variables from the global climate and observing society. And here we are looking at developing new methodologies that would not depend anymore on the sampling of local data in the field. And here it is based on this EU LUCAS large soil databases. And here you see it's an areas in northern Germany. And basically here it's the same observations as previously. So on the top it's the airborne imagery with a 2 megapixel size. And at the bottom it's the Nmap simulated imagery with a 30 megapixel size. And basically we still have, we are still able to retrieve quantification in organic carbon with a certain accuracy. Topsoil water content is also a very important parameter. And here it's the same if we look at the topsoil moisture content. So this is optical remote sensing. So please be careful because from optical remote sensing, the signal penetrates the surface maybe maximum 50 microns. So we are really talking about the top surface, the water content in the top surface. And based also on typical spectral characteristics of water content, we are able to map soil moisture variations and to minimize these variations for digital soil mapping. And come close to the end, here I wanted to show an example on soil erosional stage mapping, so looking at soil degradation. And here this is an area in middle Spain near Madrid. It's a bit a hilly area, and you see through, how do you call that? Through erosion processes, tillage erosion mostly. You see the top soils are removed at the top of the hills, and the lower soil horizons are at the surface. And then in these areas, basically the yield and the crop production is very much lower. So we developed a model based on these soil erosion and accumulation stages. And using a support vector machine classifier, we are able to map the soil erosion stages through the airborne area. And here another examples on surface processes mapping and monitoring that I like a lot. So here we are looking at Namibia, Kalahari regions. It's lots of pans, clay and soil pans, and we are looking at the soil pans. It's a very dynamic object. You see the pictures at the top. In 3 days, we had some rain standing, and 3 days later, the rain was, this standing water was gone, and already the salt crust was building. So here we did an interesting study that is showing the synergy between multi and hyperspectral imagery. So here on the left, you see looking at the change magnitude, looking at 30 years Landsat imagery. And in the middle, looking at the major crust types mapped from Hyperion hyperspectral imagery and different types of salts, halite and gypsum. And on the right, you see we were actually also able to map the gypsum content at the surface. And based on this synergy between these temporal changes from multispectral and this accurate determination of hyperspectral, we were able to also make some new knowledge into the salt pan cycle of this object. So it was a very interesting study. And to finish with the applications, I wanted to show these last examples because for dry lands is a big thematic. And in hyperspectral imagery, one of the strengths of hyperspectral imagery is that we can differentiate this arid vegetation cover from soils and from the green vegetation, of course, which the multispectral satellite cannot do. And so this is one of the power that, thanks to those hyperspectral sensors, you can detect vegetation cover in a much better way, especially for dry lands. Based on this spectral signature of dry vegetations at 2.1 micron here on the right. So some short perspectives and conclusions. So I wanted to make a summary of where you can find those new Spaceborne products. So what is really available nowadays? In summary, so you have those 17 years historical data from Hyperion that are downloadable from the Earth Explorer tools that I wrote here. Then you have 20 years CRISPR imagery that is actually still flying. So actually you can still write requests and order new data. It covers only the visible near infrared. So it depends what is your application. But then since, let's say, June this year, the websites for which Prisma product can be accessed for free is open for registration. So I wrote again the website link here. It is very easy. You have to fill out a license form, and then you get a registration, and then you need to sign in to log in. And then you have either you can browse the archive and see all the imagery that is already acquired. You can ask to download it, and then you get it 24 hours later. And they have some limitations in terms of the number of download or in terms of the number of new requests that you can do. But it's just, I mean, it's a mission that is already flying since 6 months, and we are completely overwhelmed with the number of users. So, but it's good data, and we are very happy that now we have access to this type of data. And now, so one word about DESIS. So DESIS also, so since actually October, so it's very new. The DESIS data with full spectral resolutions of 2.5 nanometer available. So it covers only the visible near infrared. So that would be more for water or some specific, I don't know, vegetation or mineral applications. And here I wrote the link for the DESIS data access. So actually now we can have fun. And here, just to show an examples of Prisma reflectance products that we asked. So it is an agricultural region in northern Germany. This is where we did this soil organic carbon maps. And you see it's a reflectance products, what they call L2D, so geo-corrected reflectance. So just to show what is actually out there now. And it shows also the perspectives. I'm really sorry, like it's never happened. Multitemporal hyperspectral spaceborne observations. So it's really something very new. We never had this possibility, or not so much. And I think now it's a new paradigm because it's great perspective for science applications. We can do dynamic processes. And plus, for each of these imagery, we have the hyperspectral capabilities and this identification and quantification of surface constituents. Except now it's technological and methodological challenges. First, it's big data. Each hyperspectral imagery is 1 gigabyte from Prisma imagery. And if we have multitemporal 1 gigabyte, it makes a lot. And then we have 4D cubes. So we have 3D cubes, which is typical of the hyperspectral imagery. And 4D is the multitemporal data. So we have to think at new ways how we can do that, new ways of being able to take this whole dimension into account. So as a conclusions, I would say applications of hyperspectral imaging in geoscience are very mature because developments are since more than 30 years. And because at the start, I mean, it's for geological exploration that hyperspectral was invented. So there was large combined efforts from the community so that there are new wealth of spaceborne sensors put in space. And now they are just beginning to be available. There are also big efforts from the community of reference databases. So I did not mention it here, but we did IEEE with my colleague Ayal Bendor since 6 months, an IEEE Standard Associations working group on defining standards and protocols. Please, anybody who is interested to join, it's international. We have 50 people participating from all over the world at each meeting. Because it's a big issue, we want to develop those big global reference databases because now we have those satellite databases. So spectroscopy from space is a high potential, but full majority is not achieved. We still have developments to do at the methodological and algorithms level. And also we have a new challenge coming with this 4D paradigm, hyperspectral plus multitemporal. But all in all, one really has to see it's now a new era. I completely believed it for the up-to-date delivery of surface mineralogical informations. And I think it will be a game changer, difference from what we have been doing in the past 20 years. So thank you very much for your attention.
Thank you so much, Dr. Sabine. A great presentation, a lot of information that we bring today for us. So can we start the discussion or you need 2 minutes before we start?
Yeah, I'm sorry because my telephone has been the whole time ringing, which never happens. So but okay, let's, no, I don't need a few minutes, I'm fine.
Okay, so we are going to start. Okay. I had a question myself. You start your presentation talking about the challenge that we have when we use remote sensing and also hyperspectral data. So I would like to know a little more about this challenge and how can we deal with this challenge?
Big question. It's actually what we have been working on the past, I would say, 10 years. Because most of our research, we developed new algorithms, now new things, a bit to extract this vegetation cover and to remove it from the signal to be able to map the soils. And we have another project now where we look at removing the moisture content from the signal so that we can extract the soil mineralogy too. So those are really new things that are not yet operational, that's the point. So we have been working on radiative transfer modeling issues and also all these unmixing. There are lots of methodologies out there. The lecture did not allow to have a lecture on methodologies for hyperspectral. There are lots of methodologies. Maybe in particular, I can cite this unmixing methodology, which is about separating the different contributions in the signal, and which is also a big avenue for the future. And now there are new ways, or some ways, to extract those members on the automatic way. So it's a big, it's actually what is doing the research since 10 years, those challenges.
Okay, thank you. Daniel, would you like to take the floor?
Okay, Rosa, thank you. Thanks, Veraldo and Jefferson, for the invitation. Congratulations, Sabine, for the nice presentation. You show several applications of hyperspectral remote sensing. Maybe if you could make a comment on the products, not the basic products like surface reflectance or sensor radiance, but in your opinion, in your view, how are the unique products to be generated by these planet missions when compared to multispectral observations?
Yeah, for me, it's a very good question. It's a question we are discussing a lot. Maybe you know I'm part of a mission advisory group for the SHIME mission, and it's always a question we get. So I had time to think about it. So for me, the unique product of hyperspectral, this is, for example, I didn't show it, but was different soil mineralogical map, like soil moisture map, soil organic carbon map, clay map, because this is an information that we really cannot do from multispectral, but without reference databases. I mean, from the spectral signal of hyperspectral, automatic processors now are able to derive those maps. So this is the plus. And I think to go to the quantitative level, we need those reference database to run model calibration. And this is another step that is not yet automatic now. But hopefully by the time of SHIME and SBG, this is what we are discussing now, but by the time of SHIME and SBG start, we have algorithms that deliver those L3 products, so the soil maps, mineral maps, automatically at the quantification level. So this is the status of a discussion now. And now for, I would say, SHIME, not for SHIME, sorry. Now for NMAP, PRISMA, so the situations of now, the missions of nowadays, I think the plus products are all those mineralogical products that are automatic, but then they are semi-quantitative. Yeah.
Another question is sometimes for some applications like crop disease, here in Brazil, for example, over soybeans, the question is related to your 4D cube in your slide. Even with a high spectral resolution, sometimes we need to increase the frequency of observation, high temporal resolution. If you don't need a satellite constellation of hyperspectral instruments, and this is a problem. Do you believe that it's possible to connect the unique information from hyperspectral remote sense with the information provided by the multispectral missions, like Sentinel or Landsat?
Yeah, good question too. In this study in Namibia, in this last paper, this is what we tried to do, and we looked at one season of, I think it was Landsat. Actually, it was not Sentinel-2, but it was 3 years of Landsat imagery, and we had some field hyperspectral end members. And actually, when we tried to make a multi-temporal mineral mapping based on trying to link this Landsat imagery with the field hyperspectral members. And we do have some, let's say some things were possible and were working well, but there was one conflict. For two mineralogy, of course, there was a conflict. And multispectral cannot do it. And just... But for me, that would be the idea. Basically, we would have, let's say, Sentinel-2 every 5 or 10 days. So I don't know, 10 Sentinel-2 images, and every 4 Sentinel-2 images, maybe 1 hyperspectral image. So something like that. And maybe somehow we can calibrate at the time of where we have hyperspectral imagery, the multispectral, and then follow the monitoring. So that would be something like that.
Okay, thank you.
Jessica. Your audio is so low. No. Can you try now? Again?
Yeah, but I've seen she wrote in the chat, no? Or is it somebody else?
Yeah, I sent a question in the chat that someone that is attending the meeting asked. So this is, thank you, Jules, Sabine, for the presentation. How would you difference between active and passive hyperspectral signal analysis, and which, in your opinion, is the better adapted to soil moisture analysis?
Yeah, very good question, actually. Because we did write a proposal on this with a colleague from Belgium. Well, for me, we need both. For somebody who is working on a soil moisture, because it is not the same information, definitely. Because the active sensors, they look deeper in the surface. It's a different soil profile. The passive sensor, so here hyperspectral, multispectral, the same. We really see just like the top surface, and for me it's a different information actually. So actually we should couple both like soil moisture to maybe get a better new insight into, I don't know, permeability or how the moisture is circulating in the soils, or new insights on hydrological processes. For me, it's not that one is more adapted than the other. Well, of course, the radar has more possibility because the radar can have different, actually different wavelengths and different depth. And the hyperspectral is really just the topsoil moisture. So that would be the differentiation.
Yeah, thank you. Jessica, can you resolve their problem? It's still slow, the sound.
I don't know.
Can you try speed just a little higher? I don't know.
Okay. My question is, what you the best starting point to work with hyperspectral data sets and imaging? And other question, any open source software or toolbox available?
Yeah, well, other than NPAP box, I don't know. But this is why we have been working on this NPAP box. It's more than 10 years. It has been a very long development. And it is, to my knowledge, the only toolbox for hyperspectral imagery that I know that is open. It's open source also, the NMAP box. So it's not only an open tool, but also open source. And I know, let's say we did the NMAP Sol Mapper, so the EnsoMap algorithms, which is also open source and on the web. And I know that EnsoMap has been used for the past 10 years because it's on the web and because it's an easy software. Actually, it's not so not anymore, I would say, state-of-the-art algorithms, but it's operational, repeatable. And I know that there are people who use it for education and teaching purposes also. And also, but real researchers now don't use this type of operational softwares. They use their own softwares to have better results. But I know actually in Germany, there is now a big momentum at the EU level also to actually integrate those remote sensing new products into how the federal institutes produce soil map in Germany. So we are not anymore in academia. We are at the level of administrations. And now those algorithms like EnsoMap are now very useful to these administrations. And this is the next step. And this is when the science is going into, administrations and. But from my knowledge, those are the only open source softwares.
Okay. Sabine, I had a question about pixel size. You talk about some applications about identify some contaminations, like, for example, heavy metals and so on, small anomalies. So how the pixel size impact that identification? Because it's small contaminations, when you have a mixture in the pixel, I don't know, I think it's a challenge to define the pixel. I don't know, it's probably you run some experiments trying to simulate a pixel size and also to try to establish the limit of that identifications.
Yeah, very good question. With heavy metal contamination, it's a bit difficult because I don't know if you have seen in my presentation, but we actually heavy metals in itself do not have a spectral feature. So it's not a direct identification. It's we identify it through proxy. Proxies like iron oxides or and I believe the spatial resolution makes a big difference in this identification. And most studies that I have shown, they were with airborne data, so airborne data with very high resolution. And the spaceborne data, we are making some simulations now to see what we can see or not. I think, of course, when we go to 30 meters, there are some loss. I think there is no magic here. When we go to 30 meters for really small processes, then we lose this this level of detail.
Yeah, thank you. We had a lot of questions also in the chat. Lenny, do you have some questions, or would you like to help me with?
Okay. Oh, it's about my question. Is Danielle Holmes? Is there any plan to build a processing hub like GEA to deal with this data?
Yeah,
dimension?
good question. Like the Google Earth, I would say not. At least not yet, or not that I heard of. But I think Google Earth is also adapted to hyperspectral. I have one of my students. He did his last paper with Google Earth. So he did, what did he do? He used Google Earth to do automatic spectral angle mapping.
Spectral map.
Yeah, does not work for all algorithms. Yeah.
I believe after the launch of the satellites, this issue will be solved. Yeah.
It's a big problem, those algorithms, because now all these data are available, and if we don't have suitable algorithms for people.
Mm-hmm. Sabine, I have another question for these planet missions. Signal-to-noise ratio is a big problem of a hyperspectral remote sensing. If you don't have a good instrument in terms of signal-to-noise, it would be possible to detect absorption bands, mineral absorption bands, leaf water absorption bands with quality. Do you think these planet missions have solved these problems in terms of signal to noise?
Yeah, tricky questions. I'm not sure what to answer. Yeah, let's say, good question. Let's say with Nmap, we hope that we get a higher quality than, let's say, Hyperion, for sure, hopefully. But yeah, I'm not sure what to answer. Normally, in each for the Spaceborne missions, we in SHIME, we have raised the requirements for the signal-to-noise ratio by 2, which has been big issues for the industrial consortiums the last year. They had to remove one of the design. So let's say we try to put higher and higher requirements to the SNR at each mission. What comes at the end?
Yes, the problem is the shortwave infrared interval.
Yeah, exactly. Yeah. The problem is, it's physics. It's physics. You put the it's channels of less energy, and you put small pixels, and then the signal-to-noise ratio is not so good.
I have another question on the screen by Gush. Hyperspectral data is not frequent. What's the solution for the availability of the data?
I would say, the links that I have given are. This has always been a big problem of hyperspectral imagery, that the data were not available. And I think now, with Hyperion already, CRIS is only visible in infrared, so it depends on applications. But I think with Hyperion and now with Prisma, and we hope that if now there is Prisma and ISWI, for me, the solutions for more availability, it's all these missions a bit together. Because one mission will never be able to provide the coverage that real processes need, waiting for this next Sentinel or Landsat hyperspectral missions. So we'll be in the combinations of all these national missions, and basically the solution for its open data policy, which is not obvious and not possible for everyone.
Jessica, can you read the next question, or
Okay.
you can ask something if you want?
The question from Marcus, correctly, as in understanding it, only the Galfen 5 satellite is able to carry out systematic observation of the Earth.
Yeah, I'm not sure what you mean with systematic observations. I think, honestly, right now, I don't remember what is the revisit rate of Galfen 5, but I think Galfen 5 is just like the others. It's just physics, and I just remember Galfen 5 has 2 sensors, like Nmap, so one in the VNIR and one in the SWIR. So it's 2 sensors combined. And I'm pretty sure it has got also a typical revisit rate, so like the other satellites. So I don't really understand the question. I think it's not better or worse, or it's at the same level than all the other missions.
In relation to the Shimalski's question, I'm not sure, but China has a satellite constellation of hyperspectral sensors with.
You mean? I see what you mean, with several sensors.
Yes, it allows almost daily 3-4 day coverage.
Yeah, but not hyperspectral.
Yeah, it's in the visible infrared.
Okay.
I'm not sure if more than 40 bands.
Yeah, okay, it's a good observation. Of course, another solution is to have several satellites. Because it's something we have discussed at the beginning with Simon. So I don't know, if we envision a series of 5 satellites, then at the end we have 1 imagery per week. But then it's a question of funding, and this is true that but those Galfen missions, they are not all open source. So I don't really have, neither myself have access to the data, or I was offered, I can have a sample data set, but I cannot answer, yeah.
Thank you. Someone of you have another question? Daniel, Jessica? No.
Yes, I have a question related to in relation to the SWAT. This do you think it's to be possible over the next decade, maybe, to have a hyperspectral mission with a large SWAT width? Because the problem of the data availability is related to the size of the sampled areas, the SWATs. For example, for a map, I believe it's 30 kilometers. Do you believe that's possible to have a mission with the issues of data transmissions, like a Landsat mission, but having high spectral resolution?
Yeah, or actually, I would say my answer is yes, because actually in SHIME, but I don't, now I don't remember the numbers. They have a very wide swath. They are thinking at some ways to have a very wide swath.
The old history mission is supposed to have a large swath width, more than 100 kilometers.
Yeah, now I don't remember. I don't have the numbers in the mind. And I know in SHIME, I don't want to discuss it maybe too much because maybe it's not yet like approved or something. But SHIME is looking at very wide swath. So actually it's a very good question and very relevant.
And it will be nice because if you have this type of mission, we would have global products like canopy water content for the entire global, the entire vegetation cover.
Yeah, I think it will be a while because
you'll be unique.
Yeah, I think this will be not before SHIME on SBG, because with the current missions we have once one image, once one image, once one image, and so global mapping maybe yeah. Or maybe from Sentinel-2, because Sentinel-2 has got some really nice capabilities. I'm looking at the question now for biomass and nitrogen monitoring. So Hyperspectral has got this capability in all cases. But actually in Sentinel-2, sometimes we have nice studies where they actually can do it quite well. So I don't know, maybe Sentinel-2 at some point can do it. Because if you have a model that is calibrated with field data, then if this is based on a spectral modeling, then sometimes we can live with less spectral bands.
We have another question in the chat. It's from Antonio Leite. Thank you, Sabine, for the inspiring talk. Do you believe that the biomass estimation in nitrogen monitoring in agriculture fields can be carried out accurately, but using a perispectral remote sensing?
Yeah, biomass is always a bit a stretch. So I answer maybe first to nitrogen. I think nitrogen monitoring, yes, because there are some studies now that are able to do it. And biomass too, but you need some, yeah, bit more modeling, I believe. Yeah, I think it's, I did not focus my talk on agricultural parameters. But yeah, in all cases. Yeah, although, as I said, biomass, I think there's always a bit of stretch from the remote sensing data.
Okay. I was thinking here about how to apply this hyperspectral data, imaging, also data, in an operational way. So, for example, we want to monitor in an area about degradation or about anthropogenic issues. And how do you think we can deal with this problem? How can you think we can monitor in a continuous way this kind of environment in a way we think in an operational way, in order that, for example, governments take decisions about policies and something like that?
I think, well, for me, there would be always this one way of identification of hotspots, for which especially this capability of looking at changes in this dry vegetation content. This is really something that hyperspectral can do better than the multispectral, and maybe identify like hotspots where it's degrading more, or maybe from the soil quality where we see the soil changes. And yeah, well, one would is to establish a monitoring program with regular acquisitions of data, looking at changes. Yeah. But it's more, yeah, it's more energy, hyperspectral imagery. That's the point. That we have to deliver some more algorithms to users so that they can do these tasks without being an expert. Yeah.
Okay. Jessica. Okay, Lenio, go ahead.
Okay, I have another question. We have another question on the screen. Is that possible to study air pollution with hyperspectral remote sensing? My colleague Bikoff.
Yeah, maybe I'm not the one to answer that questions, because they are, and also there are other satellites that look at gases and which more narrow spectral bands, more like Sentinel-5 or something, or greenhouse gases emissions. One thing I can say is that, for example, in EMIT, and this has been demonstrated in Israel by IR, also in other countries, they can look at air pollutions in terms of big particles, like sandstorms or content of sand in the air, but not. But it was more like an based on modeling and some surface data. Yeah, let's say I would say I'm less the experts to answer that question. I'm not sure that the narrow, the spectral bands are too wide.
Rosa.
Okay, Jessica, can you help me with the last question, please?
Okay. The question from Aggeneys. Can we manage plant disease with this technology? And how can we observe this type of damage in crops?
Yeah, same answers. Let's say I'm not the big experts for plant mapping, but I've seen papers where we see stress on the crops. Maybe Leneo do better than me for this answer. I've seen papers where we see stress in the crops through a different slope of a red edge at 0.67, and so through changes into chlorophyll content, I don't know, anthocyanid content, through changes in this plant biochemical parameters.
This is Sabine, this is a good question of crop disease, because especially for crops like soybean, in Brazil, for example, the disease over soybean fields have a strong economic impact. And when we have crops with a short cycle of development like soybean, time is very important. To increase the frequency of observations is important. So it's important to have, for this case, it's important to have not only high spectral resolution, but high temporal resolution. And it returns to my first question, how to increase, how to fill the gaps of the planned hyperspectral missions using multispectral data sets, for example. That's a problem for some applications.
Yeah.
There's another question on the screen. Daniel Gomez, what about water analysis? Is it possible to determine water components like sediments, dissolved organic carbons from hyperspectral satellites, or there are limitations imposed by Sanglint or other issues?
Yes, absolutely. I was not part of my talk because I focused on arid lands, but there are very nice examples of the use of hyperspectral imagery for sedum, sediments, identification of a type of sediments also in water. And these people actually now work with DESIS data, because DESIS data are they do not need the shortwave infrared. And DESIS data have a very high spectral resolution. And now they are making some like test samples with DESIS data if it works well. With airborne data, in all cases, it has been very well demonstrated, from my impression.
Okay, so I don't have more questions in the chat. So I would like to say thank you for all the attendances we had. There are people around Argentina, Azerbaijan, Brazil, Denmark, Ecuador, Iraq, India, Japan, Panama, Philippines, Serbia, UK, and Norway. So people all around the world will here attend this great presentation from Dr. Sabine. So thank you so much for being here, delivering this lecture. Thank you so much, Jessica, and also Lenio for helping me sharing this session. So I think for now is that. Remember that we had another lecture in the afternoon here in Brazil, time from Brazilian 14. So thank you again, and have a nice evening, afternoon, morning, wherever you are.
Thank you again all, and thank you to all listeners also that you bared with me. I'm very excited that you could all listen. It's nice. Yeah.
Thank you so much, and we'll see you in the next edition. Bye-bye.